Hello. This video is going to give a brief overview of the design and construction of my fencing test box. This isn't really a tutorial on how to build one yourself, but if you wish to do so, the included resources in the description should be enough to get you going. And if you have any questions about it, feel free to leave a comment here or ask me about it anywhere else, really. So that being said, let's get started. So, just to quickly explain what this is in case you aren't very familiar with fencing, the sport makes use of electronic scoring. So our weapons each have a button on the tip which attaches to wires running down the blade and into a socket at the guard. The socket connects to what we call a body cord, which is just a large cord that runs through our jackets and connects in the back to a longer cord that feeds out of a reel. Some weapons also have what's called a lame, which is just a conductive jacket or vest. The reels are provided by the tournament organizers or fencing clubs. However, the blades, body cords, and lames are personal equipment. Obviously, we want to keep our equipment well maintained, so it is useful to have a test box such as this, which is, in essence, just a multi-channel ohm meter designed for measuring fencing equipment. So, onto the box itself. It is made from a 3D printed housing. It has a power switch, 3 push buttons, which are used to navigate through the menu and test pages, and an OLED display to show the menu items and measurements. The display is protected by a piece of laser-cut plexiglass. Then, of course, we have the sockets and tabs that the equipment will be connected to. Now let's get into how this works. The box is run by an Arduino Nano powered with a 9-volt battery. Starting with the body cord, it measures the resistances of each line of the cord by feeding a constant current through the wire. So we have an electric current coming from our constant source, passing the ground through the wire. Now we measure the voltage where the current enters the line and assume the end where it exits to be at 0 volts. In practice, this won't necessarily be the case as the other end attaches to a socket that might not have 0 resistance, thus slightly increasing our measurement. This factor will be accounted for later, but for now, we can ignore it. So, we have the voltage difference across the wire and the current flowing through it. Therefore, we can use Ohm's law, V equals IR, to find its resistance. Since body cords have 3 lines, and we want to be able to measure all of them at once, we want to have 3 of these units, 1 for each line. Now, in addition to measuring the resistance of the wires in the cords, we also want to be able to measure the resistance of the wires in the blades. To do this, we will need to plug one end of the cord into the weapon and the other end into the box. This means that we want to measure the resistance between 2 lines on the same side of the cord. In order to do this, we have the right side being A line, ground, C line, and the left side being ground, B line, ground. This means that on the right side, we can also measure AB and BC resistances, which is exactly what we want for the blade tests. Now let's take a closer look at what these units actually are. We have our constant current source made by putting a resistor between the V out and adjust pins of a voltage regulator. However, we can't just plug these in and start using them. During the early stages of prototyping and testing various circuits, I discovered that if you were trying to measure all 3 lines at once, the readings on the lines would interfere with each other. Unfortunately, this proved to be a hardware issue that could not be easily corrected for in the code. The best solution that I found was to put transistors between the current sources and output sockets. The transistors serve as digital switches, and the code makes sure that only one of them is allowing current through at a time, thus stopping the measurements on different lines from interfering with each other. This diagram shows one of these units. It takes in 5 volts and produces the current as previously discussed. The current first goes to the transistor controlled by a digital pin on the Arduino, then, if permitted, continues on to the socket. Also connected to the socket is a wire leading back to an analog pin in order to read the voltage necessary for calculating the resistance. So this is the code that's running the box. It would add too much to the video to go into full detail, so I'll just give a rough overview of what it does. We start, of course, by including the necessary libraries. Then we initialize the display and declare constants. Now, the way this code works is that I've written at least 2 functions for each menu page. There is an initialization function, which runs once when the page is changed, and then a page function. The main loop will constantly check what the value of the page variable is to then run the appropriate page function. This effectively causes the page function corresponding to the page variable to loop until that variable is changed. Additionally, most of the pages also have helper functions that will run within the page function. For example, we have 3 helper functions, each designed to check if one of the buttons has been pressed. These will, of course, be used in all of the page functions. Another commonly used helper function is called highlight, and inverts the color on one of the lines of text, thus showing which menu option is currently selected. Now here, we have the initialization function for the home page. It starts by clearing the display, setting the cursor to the origin, setting the text color to 1, the options are 0 for off, 1 for on, and 2 for invert, and then prints the page name followed by the 2 lines of options. Then it refreshes the display to show these changes, sets the line variable to 0, and then sets the last page variable to homepage. Now we go on to the actual homepage function. The first thing it does is use the last page variable to ensure that the initialization function runs if, and only if, the page has just been changed to home. Then it checks if any of the buttons have been pressed. If the left or right button is pressed, it increments or decrements the line variable by 1, then highlights the corresponding line. If the select button was pressed, it changes the page based on the current value of the line variable. These are the most basic initialization and page functions, but all the others will have essentially the same structure. The next several are the settings, main, and subpages, which allow each test page to be enabled or disabled, resistance graphs or the words good, iffy, or bad to display with the resistance values, as well as an option to store the current settings in permanent memory so that they will be retained even when the box is turned off. Now we move on to the chord test page. We can see that the test pages make use of a lot of helper functions for taking the inputs, calculating the resistances, producing, updating, and displaying the values, graphs, etc. The initialization functions are also quite a bit longer than for the home page, though examination will show that there isn't really anything too fancy about them. Since the chord and blade test methodologies were already discussed, I won't repeat them here, but suffice to say, the main addition to these pages are the helper methods running their respective tests. Aside from those, we also have the Lemay test, which is essentially the same as the chord test, but runs constantly on the A line with the other lines off. The zero page, which records the line resistances of the chord you are using and automatically subtracts the relevant values from future measurements, and the cross test page, which checks for cross connections in the chord. Now we have the main setup function, which runs only when the device is powered on. Since we wanted the configuration settings to be changeable, they cannot be hard-coded and are instead stored in and read from the permanent memory. Incidentally, this means when the box is first assembled, a separate bit of code must first be uploaded in order to provide the initial settings. Then we have the main loop, which, as previously discussed, essentially just loops whichever page function corresponds to the current page variable. Hopefully this gives you a basic idea of how things work. If you want more detail, the full code will be linked in the description and the comments should help fill in what I skimmed over. And, just for completeness' sake, here we have the configuration code. I have two different presets here, each written into their own function, configure A and configure B, so that only one letter in the code needs to be changed in order to switch between these presets. Since the configuration only needs to run once, everything is in the setup and the loop is empty. All it does is check what the value stored at each given EEPROM address is. If that value is different from what we want, it is changed. Then it prints out what each of these values is to confirm that everything was successful. So now let's revisit the earlier problem of accounting for internal resistances of the device, as well as the currents being slightly off their calculated values. In order to do this, I've made these wires, which consist of different resistors connected to these alligator clips. So we can connect these to our sockets, as well as to the multimeter and the oscilloscope in order to take these measurements. So let's start by measuring the resistance of the multimeter leads. So I seem to be getting about 0.8, 0.9. I'll just write that down. And now let's start doing the wires. So the blue wire is about 22.8, 22.9. So when we subtract our leads, I'm going to say that our blue is 22 ohms. Then we have our white. So our white is 1.8, 1.7, about, or sometimes 1.9. So I'll say between 0.7 and 0.8. So our white is 0. 0.9 ohms. Maybe 1 ohm. That one I'm a little bit less confident in because it's going between 0.7 and 0.9, but we'll say it's about 0.9 ohms. And then we have yellow. Okay, so here it seems to be between 5.4, 5.5. So, okay, we subtract, say, 0.8 from 5.4, and that gives us 4.6. Okay, so our yellow is 4.6. Okay, and so now that we've done that, time to bring in the oscilloscope. And I'm going to start by connecting each of these, or each end of these wires to one of the plugs. And let's connect that to the first oscilloscope channel. So here I've taken those wires that I made earlier and plugged them into the box, and I'm running the chord test on it. Now also I've connected the oscilloscope probes to each end of these wires so that I can measure the voltage going across them. And so we can see that displaying on the graph on the scope. Okay, so let's pause that so we can take a closer look. And so we can see basically that we have so yellow is channel 1, or the A line in this case, and purple is the B line, and blue is the C line. So, okay, we have the A line turns on, you can see, then it turns off, and then the B line comes on, then that goes off, and the C line comes on. And the C line stays on the longest because if you recall from the code, when we start, we just turn on the A, we measure, we turn on, and we turn it off, we turn on the B, we measure, turn it off, we turn on the C, we measure, and then we do a bunch of other stuff as well. And then we only turn it off right at the end, right before going on to A. All right, and so now this also kind of gets us to the point of accounting for those kind of issues that were discussed earlier, where the circuitry will potentially have a non-negligible resistance, and then also the readings on the analog pins aren't exactly super accurate. And so this kind of takes us to the limits, I think, of what we can do with just this device without doing anything else really to, like adding, say, an additional circuitry to make the readings more accurate. And so what we can do here is we can see I'm taking measurements of the amplitudes for these square waves. And so what I can do from that is I can say, okay, so let's take line 1, for example. I have 86 millivolts amplitude, which means when it's measuring the resistance of that line, it's measuring there's 86 volts going across the wire. And I have the white wire, or the 0.9 ohm wire, going across line A. So what that means is, in order to get the current that's on line A, I just take 0.086 volts, and then I divide it by 0.9 ohms. And this gives me about 9.56 times 10 to the minus 2 amps, or 0.096 amps. Now the problem is that this isn't uniform, or this doesn't stay the same. So what I mean by that is, if I disconnect the yellow wire, which has a resistance of 4.6 ohms, and I replace the white wire with it, so now the A line has the 4.6 ohm resistance across it. And let's resume so I can take some more readings. And okay, now I need to rescale. Okay, so now the voltage on the A line is 336 millivolts. So that's 0.3, okay, it's 4.4 now, 3.6. Okay, so it's around 0.34, say. So 0.34 volts. And we divide this by 4.6 ohms. And that gives us a value of 0.074 milliamps, which is a bit smaller than the value we got previously. So it ideally shouldn't be the case, but again, this is a real-world circuit, not a theoretical circuit, and in particular, it's made just kind of to be cheap and easy. It's not supposed to be insanely accurate. So yeah, we see basically that the current will change depending on the resistance of the wire that's going across it, which is not ideal. But for our purposes, we don't need ideal, because ultimately this isn't supposed to be like a super rigorous piece of testing equipment. It's just to kind of give a rough idea how the stuff is. And in particular, we can calibrate it to suit our purposes of, is the resistance good enough for to be quote unquote tournament legal, or, is it good or bad, essentially. And to that, the tournament limit is around 1 or 2 ohms, so I'm just going to use the white wire, and I'm going to calibrate for this 0.09 ohm resistance. So let's connect that back up. And so we can see that the cord is reading, or the cord test is reading a resistance of 0.7. So 0.7 ohms right there. And so that just means basically that I need to write a piece of code that will, or I'll need to modify the code to correct for that. And now I could do, for example, so already I had, when I made this originally, I had, just sort of guessed at the current value. I mean, in this case, actually, it was based off of the previous box that I made. So now I'll go in and I modify the I modify the current value in there to align with it. And then what I do is I'm just going to correct the reading. So I take, for example, I add the correct current, and let's say now it's reading maybe 0.8 for some reason, because the analog pins aren't super accurate or whatever. Then all I'm going to do is I'm just going to basically take a scaling factor. So I say, like, okay, it's reading 0.8, and I know that it should be reading 0.9. So I'm just going to divide 0.9 by 0.8, and I'm going to get this number, which in this case is 1.125, and then I'm just going to multiply that by whatever the reading is. And so what this means essentially is I'm calibrating it to be reasonably accurate in the range of 1 ohm, and then the further you get away from that, the less accurate you get. Which is okay, again, for our purposes, because as it starts to get up even to 5 ohms, then we know, okay, like, this isn't great for tournaments. And even up to the limit of the device, which is 25 ohms, mostly they still work. But if you're getting up till around 10 ohms and stuff, okay, maybe you should clean it. But again, it's rough limits. It's not like when something hits exactly 8 ohms, 10 ohms, whatever, that there's a problem. So the fact that it isn't super accurate in those in that range isn't really a huge problem. And similarly, if it's under 1 ohm, as it goes down to like 0.5, 0.1, 0.2, even if it's not super accurate there either, although it will be more accurate than, say, like at even 5 ohms, just because of the fact that it's closer. Even if it's not super accurate there, again, that's not a huge problem because that's reasonably below our limit. So, yeah. Overall, it's not ideal, perhaps, but it serves our purposes at least. And in the future, maybe I'll revisit this project and see if there's a reasonably effective way to make it more accurate. But for now, this will suffice.